So let's try to understand a more finite state machine. Okay, let's say we are trying to convert a level signal to a pulse signal. A level signal is basically a long pulse, right? 0 0 1 1 1 1 1 1 0 0. A pulse is only one clock period wide, so 0 0 1 and then 0 0 0. So how would you do this? Now remember, a state machine consists of three parts, right? Next state logic, state register, and output logic. Let's say initially you start at state equals to 0, right? If your input is 0, that means you are not detecting any level signal, then your output is 0, right? Your output is 0 as long as you stay in state 0. When you detect a 1, you change from state 0 to state H. When you change to state H, your output becomes equals to 1, alright? After your first one, if you detect 1 again, move from state H to state 1, okay? Move to the third state. In the third state, the output is 0, alright? And finally, while you are in state 1, if you detect a 0, so you detect this 0, you move from state 1 to state 0, right? You go back to the first state. While you are in state 0, the output is still 0, okay? So this is how you convert from a level signal. Notice that you have a level signal, you convert to a single pulse, like that, single pulse, right? So how can we achieve this? So that's what we are trying to achieve, but how can we do that? Now notice that according to the diagram, we need 3 states, right? 3 different states, 0, H, and 1. This is the initial state, right? So 0, H, and 1. So what we can do is, we must start by drawing state diagrams. So because we need 3 states, we draw 3 circles right here, right? 3 circles. We call them 0, H, and 1. Now we can choose whatever encoding we want, okay? In this example, we are going to choose binary encoding. So binary encoding is going to go from 0 to 0, 0 to 1, 1 0 to 1 1, okay? But in this case, we need 3 states, so we choose 3 out of these 4 states. So we choose 0 0, we choose 0 1, and then we choose 1 1, alright? We don't use the 1 0. We can use the 1 0, but in this case we want to use the 1 1, so we don't use the 1 0. Okay, so we write our encoding here, 0 0 0 1 1 1. Output. Now remember, while you are in state 0, your output is equals to 0. So let me show you here. While you are in state 0, your output is 0. When in state H, your output is 1. While you are in state 1, your output is 0. And while you are in state 0, your output is, of course, still 0. So 0, 1, 0, that's the output. While you're in state 0, if you detect a 1, then you move to the next state. If you detect a 0, you stay in 0. You stay in the first state. While you are in H, if you detect a 0, you go back to the 0 state. If you detect a 1, you go back to the 1 state. And then while you are in 1 state, you move to 0 if you detect a 0. So if you detect a 0, you move to 0. If you detect a 1, you stay in 1. Alright. So this is the state diagram. So how do you draw a state diagram? Now, hang on, let me go to the previous. So this is how you draw the state diagram. So notice that in a state diagram, you must have present state, in state, next state, out, and then comment. The comment is not important. This is the important one. 1, 2, 3, 4. Right? So we start from the first state, 0 0. So you write 0 0 here. 0 0 0 0. Now while you are in state 0, so this is state 0. Right? While you are in state 0, if you detect a 0, so you detect a 0, you stay in state 0, right? So stay in state 0. So that's why you write a 0 0 here. 0 0, right? So while you are in state 0, So 0, 0, 0, 0. If you receive a 0, you stay in state 0. If you receive a 1, you move to the next state 0, 1, which is edge, right? So this is edge right here. E, D, G, E, right? So state 0, receive 0, stay in 0. State 0, receive 1, go to next state 0, 1. Output, while you are in state 0, your output is always 0, right? Your output is 0 when your state is 0. So you just fill in here 0, 0. Okay, can you see here 0? So just put 0 and 0 here. Now, while you are in state edge, so this is edge right here. If you receive a 0, go back to 0. So you are in state edge, you receive a 0, you go back to 0. So you write 0, 0 here. While in state edge, if you receive a 1, so you receive a 1, you move to next state. So you receive a 1, you move to next state, 1, 1 right here, right? Your output, when you are in state edge, your output is always 1. So put a 1 here, 1 here. Right? So put a 1 here, put a 1 here. Third state, so state 1, right? You receive a 0, you go back to state 0, right? So receive a 0, go back to state 0. If you receive a 1, go stay in state 1. So you receive a 1, you stay in state 1, okay? While you are in state 1, your output is always 0. So put a 0 here, just like that. Okay? So once you have filled up your table, the next step is to derive the next state equations and output equations, okay? So let me draw a line here. So this is the output, right? You have to derive this equation. So let's look at your Q1 first. When is your Q? So look at your Q1 and notice that Q1 is only equal to 1 when Q1, Q0 is 1. So Q1 plus is equals to 1 when these are the input, right? So 0, 1, 1. So 0, 1 and 1. Then you put a 1 here. 1, 1, 1. So 1, 1, then 1, put a 1 here. And the rest are all zeros, right? So 0, 0, 0, 0. 1, 0. We don't have 1, 0, right? If we don't have 1, we have 0, 0, 0, 1, 1, 1. We don't have 1, 0, right? So just put an X here. What about this one? So this is for Q1 plus. This is Q0 plus, right? So for Q0 plus, Q0 plus, look at Q0 plus. Q0 plus is equals to 1 when this is your combination. Equals to 1 when this is your combination. Equals to 1 when this is the combination, right? So Q1, so 0, 0, 1. 0, 0, 1. Okay, so put a 1 here. 0, 1, 1. So 0, 1, 1, put a 1 here. 1, 1, 1. So 1, 1, and 1, put a 1 here. And the rest are all 0, right? Okay. And, sorry. Finally, P. Remember, P is 0 when... Oh, sorry. P is 1 when Q1 and Q0 is equals to 0, 1. When you are in state... Remember, when you are in state edge, the output P is equals to 1. So 0, 1, 0, 1, then your P is equals to 1. And it doesn't, you don't care about anything else, right? P is equals to 1 when Q1 and Q0 is equals to 0, 1. So put here 1, and then the rest are all 0, right? 0, 0, 0, 0. So 0, 0, X. And this is how you write the equation. So this is going to be LQ0, this is going to be L, and this one is Q1 bar Q0. Okay. So once you have these equations, you can draw your you can draw your schematics already. Okay, remember, you are going to move from 0 to 0 to 0, 1 to 1, 1, right? So how many flip-flops do you need? You need 2D flip-flops. So draw 2D flip-flops. Okay. D, so Q1, Q0. Okay. So it's going to be 0, so it's either going to be 0, 0 or 0, 1 or 1, 1. Okay. Remember we have 3 parts, so this is your state memory. So this is going to be our state memory. Remember Q1, so Q1 is equals to LQ0. Q0 plus is equals to L. Right? L is your input. Okay, so let's draw an L here. L, so Q1 is equals to LQ0. So draw an AND gate. Okay, and then we are going to put L through the AND gate. The other input of the AND gate comes from your Q0. So connect it like that. So we're going to connect it like that. Oops. Now what about your Q0 plus? So Q0 plus is equals to L. So it's equals to L. Like that. Okay. Connect like that. So this part here is your next state logic, because it determines the next state. Okay, it determines what your D flip-flop is going to change into. Now look at P. P is dependent on Q1 bar and Q0. So Q1 bar and Q0. So put a NOT gate here and AND gate, right? Like that. So that's your P. You can either put a NOT gate here, or what you can do is sometimes D flip-flops have a second output here, which is the opposite of the complement of the first output. So they have a Q1 bar. So instead of using a NOT gate, what you can do is you can connect this Q1 bar to your AND gate. So it's the same thing, alright? So you can either use a NOT gate or you can use the Q1 bar output. And this right here is your output logic. Okay. So notice that you always have 3 parts here: next state logic, state memory, output logic. And it's going to be the same as so this is what you have on the slide. It's the same thing, alright? Okay. So let's see how we can design the same level to pulse converter, but this time using the Mealy approach. We start off at state 0 again, and if we receive an input, so if we receive 0, so then our output is going to be 0. So while you are in state 0, if you receive a 0, output is 0. Okay. While you are in state 0, however, if you receive a 1, so you receive a 1 here, so you receive a 1 here, produce an output, your output is also 1, alright? So you produce a 1 here. Okay. So while you're in state 0, you produce a 1. If you detect a 1, you produce a 1. Okay. And you move to the next state, which is state 1. Okay. So notice 2 things happen. While you're in state 0, you detect a 1, you produce a 1, and you move to the next state, state 1. Okay. Now, while you're in state 1, If you continue to detect 1s, so you continue to detect 1, then if you continue to detect 1, so while you're in state 1, if you continue to detect 1, then your output drops to 0, okay? So produce 0, so output equals to 0. If you are in state 1, and I don't know what happened, if you are in state 1 and you detect a 0, so let me draw a 0 here. So you detect a 0, so you detect a 0, your output is still 0, and you move to the first state, right, which is state 0, like that. So notice that you only need 2 states, right, state 0 and state 1. So let me repeat. While you're in state 0, you detect 0, you produce 0. You do not change state, you stay in state 0, right? While you're in state 0, you detect the first 1 here. So the first 1, you produce a 1 and you change state, right? 2 things happen. Produce a 1 and change state. They are happening at the same time, alright? These 2 things are happening at the same time. While you are in state 1, if you continue to detect 1, output becomes 0, right? And finally, while you are in state 1, if you detect 0, so you detect 0, 0, your output is still 0, 0, and you move to state 0, move back to the first state, right? So let's see how we can turn that into a state diagram. So 0 and the 1. You know what, I think I'm just going to draw. So 0 and 1. So we need 2 states, right? So we draw 2 circles. 0, 1. Okay, actually you don't have to call them 0, 1. You can also call them A or B, right? Up to you. Again, we are going to use binary encoding. Now notice that we only need 2 states, right? 1 and 2. So actually we can use 1 flip-flop is enough. So 0 and 1, right? 0 and 1. We don't need 2 flip-flops because we only have 2 states. Let's fill in the blanks. So while you are in state 0, if you detect a 0, stay in state 0 and produce output equals to 0. So while you are in state 0, you detect input 0, produce 0, and stay in state 0. While you are in state 0, if you detect a 1, right, you detect a 1, produce a 1, right? While you are in 1, you produce a 1 and you change state, change to state 1. While you are in state 1, if you detect a 1, so you detect a 1 as your input, produce a 0. So this is your output, right? Output. And stay in state 1. Finally, when you are in state 1, if you detect a 0, stay in state, move to the first state, 0, move it back to the initial state. So produce an output 0, right? So this is how you draw the state diagram. Let's see how we can draw the state table. So state table. Remember, for state table we need 4 things, right? Current state, hang on, alright, sorry. So remember, for state table you need 4 things, right? Current state, your input, your next state, and your output, right? Now because you only you look at your binary encoding, you only have 1 digit, right? So 1 digit, so your output is Q, right? Just use 1 flip-flop, and your output is L. Your next state is Q plus, and your output is P, alright? So while you are in state 0, your Q is 0, and your Q is 0. Now while you are in state 0, if you receive a 0, stay in 0, produce a 0, correct? While you're in state 0, your input is 0, you stay in state 0, you produce a 0, like that. Now while you are in state 0, if you receive a 1, then your next state is going to be 1, so you change to the next state. What about your output? Your output is also 1, right? So you put a 1 here. Now let me draw a line. Right. So this is state 0, right? State 0. So now that you are in the next state, because you detect a 1 previously. So let's put a 1 here, right? Now you are in state 1. So while you are in state 1, if you detect a 1, produce a 0 and stay in state 1. So while you are in state 1, you detect a 1, so I'm going to put a 1 here. You stay in state 1 and you produce an output 0. If you are in state 1, you detect a 0, so you detect a 0. Your next state is going to be 0, and your output is going to be 0, right? So output is going to be 0, so put a 0 here. And there you have it. That's all you need, right? Now from the state table, you are going to derive the next state equations and your output. Now this is pretty straightforward. I don't think you need the K-map, right? So let's look at your next state, Q plus. Notice that Q plus is equals to 1 when your L is equals to 1. So we can say that Q plus is equals to L, because our Q plus is always the same as our L. What about our output P? Well, P is equals to 1 when Q is equals to 0 and L is equals to 1. So we can say that P is equals to Q bar L, like that. Yeah? And that's it. That's your state diagram. So this is your state diagram, state table, next state equations and output equations. Okay. So finally we can draw our circuit. Remember, we only have we have 2 states, so we only need 1 D flip-flop. DQ. Okay. So this is our state register. Note, remember our equation is Q plus equals to L and P equals to Q bar L. Alright. So Q plus is equals to L. So I can straight away put an L here. Alright. The Q follows the L. So just connect the L straight away to the flip-flop. In this case, we don't need any logic gates here. But this part here, we still call it the next state logic. Okay. Next part here is output logic. We have a P, right? P is dependent on Q bar and L. Okay, so you're gonna take the Q bar, okay, and then we are gonna AND it with the L. Alright, so AND gate, Q bar and L, like that. So that's your P. So this is your output logic. So this right here is your output logic. Right? Let's try to see the difference between the timing diagram for Moore machine and Mealy machine. Okay. Remember, the states are represented by the output of D flip-flops, right? Output of D flip-flop. Okay. When you're at 0, your D flip-flop is 0 0. When you're at edge, D flip-flop is 0 1. When you're at 1, your output is the D flip-flop is 1 1 and then goes back to 0 0. In the Mealy machine, 0 1, the state 1 is represented by 1, then 0. You only need 1 flip-flop, right? Okay. Now remember, the flip-flop can only change at the clock edge. So let's say you are at state 0. Yeah, you are a Moore machine. You are at state 0. Even though your L changed to 1, you cannot change to edge. because you must wait until the next clock side. You must wait until the next positive clock edge. So you stay at 0, even though you see this L right here. So you stay at 0. When you reach the next clock edge, you check your L. Your L is 1, so you move from 0 to edge. So move to the next state. And while you are in edge, if you detect a 1 at the next clock edge, move to the next state, which is 1. And then if you are in state 1 and your L is 0 at the clock edge, you return to state 0. Now remember, in a Moore machine, the P depends on state only. Okay? In other words, when your state is edge, your P is equals to 1. So it's equals to 1 all the time while you are in this state. Right? It is. Now look at your Mealy machine. Your Mealy machine is different. Remember, a Mealy machine has a direct connection, right? From L to the P straight away, direct connection. So let's say you are in state 0. While you are in state 0, your Q is going to be equals to 0, but your Q bar is going to be equal to 1, right? So Q is equal to 0, Q bar is equals to 1. And remember, your P is equals to Q bar L, right? Q bar L. If your L goes to 1, right? If your L goes to 1, because of this direct connection right here, your P will change to 1 immediately. Your P changed to 1 immediately. Why? Because now your Q bar is 1, right? Your L is equals to 1, so of course your P is going to be equal to 1, because P equals to Q bar L. Right? So you go to 1 immediately. But when your L drops to 0, you also drop to 0 immediately, because now your Q bar is 1 but your L is 0, so your P must be 0. Alright, so you drop back to 0 immediately, and then you go back up again. So let me erase this. At this point right here, your Q bar is equals to 1, your L is equals to 1, so therefore your P must go to 1 immediately. Right, so P goes to 1 immediately while your L is 1 and your Q bar is 1. Right? So can you see the difference between Mealy machine and Moore machine? A Mealy machine, the output can change immediately, whereas a Moore machine, the output must wait until the next clock edge in order to change. Right? Now while you are in state 1, your Q bar is equals to 0, right? So if your Q bar is equals to 0, then your P is always 0, correct? So that's why your P drops to 0, and it stays as 0 all the time after that, right? So you also get a pulse here, but your pulse is your pulse have glitches in it. So that's the disadvantage of Mealy machine. So Mealy machine output has glitches, right? That's a disadvantage. The advantage of Mealy machine is you only need 2 states, so you need less flip-flops. So notice that you need 1 flip-flop only here, whereas in the Moore machine, so where's the Moore machine? The Moore machine, you need 2 flip-flops. Hang on. Yeah, you need 2 flip-flops. So you save a flip-flop, but you have glitches in your output, right?